About conferences, right now I'm speaking from the hotel from Vancouver because I'm at New Rips 2019, and if one of the speakers or some of you are here, you know, maybe we can like meet in person and chat more today and tomorrow. So it's like this thing. Let's talk about image augmentations, about images, object detections, this type of the stuff. So right now at New Rips, there's 14,000 people. Most of them are, let's say half of them are just attendees, and they're trying to understand what's happening in the academia and the state-of-the-art research and to get a vision of where we are going in machine learning and artificial intelligence. And half of them are speakers that presenting their like cutting edge work. And that's what is happening here. Cutting edge work is important, but not really. Why? So let's say there's some researcher and he has some idea, he checks it on some like benchmark data set, or maybe, you know, have some insights or some types of the problem. He presents this at the conference, and this is good. Maybe, you know, like 10 people at the end of the day, while being tired, come to his poster and like hear to him. And that's it. Most likely this idea will not go that far. We know plenty of examples in history when strong ideas, basically, you know, after research was done, it was forgotten for a few years or months or like even decades. And what's there? Like, there are a few reasons for this. Like, and researchers, in my understanding, should probably work more on like promoting their work, like through blog posts, webinars, again, conferences, and some other events. But at the same time, they should push and they should try to move their research from like some state-of-the-art narrow field to something that I would prefer to think about it as a commodity. Basically, if some strong researcher or some strong engineer can do some kind of like, you know, complex task, is not really that important. What is important for the industry and humanity in general is when some technique becomes a commodity. If we like look again for whatever, like right now is almost 2020, all of us remember this breakthrough result in competition in image classification in 2012, Balik Skrzewski. And at that point, let's say we're talking about 2012, 2013, deep learning was like cutting edge. No one knew this, like the industry wasn't using this, this wasn't a commodity. And slowly image classification picked up, and by 2014, some different like companies started using this in production, and it started bringing value, bringing money, and like bringing some value to people. And then later on, and image classification, what is image classification? Image classification is a task. It's when you take some image of something and you feed this to some algorithm, some neural network, and it predicts, okay, with probability 75%, this is dog, probability 30% is a cat. Some kind of like assigning labels to different tasks. And again, use cases, plenty of them. Many companies work with imagery data. It may be something like in the core of the business, let's say self-driving car cannot work with like good imagery. All self-driving cars like you know, Lyft, Uber, Yandex, Waymo, like Tesla, all work with imagery. So you need to extract this high-level information. And image classification is the most well-established, commoditized task. And like you are in the high school and you can solve this task. This is good. Later on, what happened? Later on, like it's good to assign some kind of like course label to the image, dog, cat, person, car. But you would like, you know, let's say image is big and your car is in the middle of the screen or the image, and you would like somehow to localize it. You either want to find bounding box that surrounds this car, or you want maybe like on the pixel level to say that this pixel is a sky, this pixel is a person, this pixel is you know, a car. And this is more fine-grained, allow you to solve plenty of other like problems. For example, like good use case, if we talk about medical imaging, you do some kind of like X-ray of your lungs, and you need to find, I don't know, like some nodules, cancer, or like whatever it is, like, or region where pneumonia is pronounced. And it's just not enough to say this person has pneumonia. It would be like better like for doctors to see a region where they can and should, you know, focus on. And this is like object detection and image classification. And these are, again, so the tasks picked up by industry and by research later on. But at this point in time, at the end of 2019, 2020, these two tasks also became a commodity. And again, like it's enough to be in the high school, I mean, maybe even earlier, to be able to solve this object detection tasks to some extent. Use cases for object detection, as I mentioned, medical imaging, like localizing different types of the issues with the health and X-ray scans, maybe like some cells, so predicting cancer, this type of stuff. Satellite imagery is very important industrial setting where you have satellite imagery and you need to find like roads or buildings, and this improves like, you know, maps. Or for example, at some point I talked to a company called Descartes Labs, and they were telling me about some interesting use case. Apparently in the United States, no one knows how many wind turbines do we have. And like, I mean, counting them, like covering all countries and feasible, but you can scan this like images, satellite imagery of the whole United States, and within one day with this like object detection segmentation algorithms, you can find all of them and estimate their number, and it's pretty powerful in this case. So again, image semantic segmentation, object detection, it's like, you know, deep learning, computer vision type related stuff. What do you need to work with them? To work with them, you need to have training data. You need like a pair of objects, image on one side and corresponding like labels, like maybe a pixel label or, you know, bounding boxes. You need some kind of label. This is good. The issue is labeling this is cumbersome. How? Because you need to find some humans. They need to label something. If, again, we are talking about street view imagery and you need to label cars, everyone can do it. But if you're talking about, you know, like finding regions with pneumonia on the images, you need doctors, well-trained doctors that are used to this, and their time is expensive, and maybe the accuracy is not perfect. And this is all very expensive from the time perspective and from the, you know, money perspective. That's why if you go to the conference called MICAI, the like biggest medical imaging conference, researchers work with data sets, I don't know, like 50, 100, maybe 1,000 images, which is pretty small. In the world of the machine learning and especially deep learning, you need and you want to work with big data sets. The premise and the big thing, like why deep learning like became a thing, explosion in this field, because people figure out that there is like in many tasks no need to handcraft features, to like do some kind of heuristics, to do like, you know, complex feature engineering. You just can find good networks and add a lot of data, and more data is better. And from my experience, it's also the case. More labeled data you have for training the networks is better. But as I've said, so we want more data, and at the same time, data is expensive. Data labeling data is expensive. There are a few solutions to this. One direction is called like semi-supervised or unsupervised learning, where you take a bunch of imagery and then you try to find some underlying high-level structure without even labels and go with this. Very promising field of research. There are some industrial applications. It didn't become fully a commodity yet, but some things here and there are already propagating to industry. Another more intuitive and more straightforward approach is called image augmentations. What image augmentation is? So let's say you have an image of the cat. It's only one image, and you have a label. This label is a cat. But at the same time, you as a human know that if you flip this image horizontally, it still be a cat. Sure, its nose will be pointing in some other direction, but it still will be a cat. And from your perspective, it's same image, same cat. We as a humans see these patterns on a very high level. It's easy for us, it's same cat. But for the network, it's different pixel values on the same locations. For your network, for your machine learning model, this flipped image, this change of your original image created more synthetic data. And then, but you can be more creative. Again, works really well with images, significantly less with text. But here you can look at this image. Okay, what else can we do? Let's rotate this cat by 5 degrees left. Can we do it? Sure, it's still a cat, still same label, and your data set increased. And here, maybe you see the pattern. You can do like horizontal, vertical flips. You can do rotations. You can do zoom in, zoom out. Still it's same cat, still same label. And you can try to increase this data set like with a lot of time. At some point when I was bored, like in summer, I decided that, I mean, like flipping and like rotating, it's kind of like entertaining, but I work in the self-driving industry. Let's add something more, maybe not valuable, but more fun. So I wrote some code that adds snow and rain to your images, because I mean, in self-driving, it's like maybe an issue. Again, for those who live in San Francisco Bay Area, weather as now is pretty bad for driving, like raining all the time, great for snowboarding, and I'm very excited about upcoming snowboarding season, but it's raining. And data that was created in summer when it was sunny, models trained on it may not perform that well. So again, image augmentations, it's a way to synthetically increase your data set. And in this talk, like at this big data conference, I'll talk on more details. Again, I covered right now what each image augmentations are, but then I should probably have some kind of numerical estimates of like what's the value of this. Like let's say we add this type of augmentations, how much better your network become, how much more robust. I will also going to cover latest research results that like from this new RIPS and from like, CVPR of this like this top conferences in the field. And again, still not enough, research is great. As it was mentioned in the introduction, I'm Kaggle Grandmaster. Kaggle is a platform where different companies, Google, Facebook, Lyft, I don't know, plenty of others, they host machine learning competitions, and thousands of people, they compete with each other for prizes and just for fun to like develop and bring the highest solution. Typically, if you look at some competition with respect to academic conference like NIPS or CVPR, you get like around 10, maybe 15 people. But at Kaggle, it's like well-established platform, and at some point, a couple years ago, it was acquired by Google. It was a big achievement for them. Number of participants is in thousands. And basically, to get to the top, you need to be not just good, like better than average. You should be better. Like, it's state of the art competes with the state of the art. There are many techniques and image-related problems to get to the top, and image augmentations is one of them. And in this upcoming talk that we'll have, like in these conferences, at Global Big Data Conference, I will also share some actual examples how winning teams in a wide range of computer vision tasks leveraged image augmentation techniques, what tips, what tricks, and what like helped them to get to the top. And I hope that like those who will attend the conference will learn from this, and not just on the like high level scientific level, but in more concrete, and these insights that I'm going to share at this conference will help you actual products that you're facing and building right now. Yeah. That's my speech. Okay, it's 1:20, and I believe this was my time. So if there are some questions by the audience, I would be happy to answer them now. No questions. Okay, what I'm trying to say, I don't have favorite architecture. I know that like even for image classification in the like, if you need to do some kind of task of distinguishing like what type of camera was used to take an, to take some particular image, you need one type of architecture. If you want to distinguish dogs versus cat, like it's another one. And so in this sense, I don't have favorite architecture, different tasks, different architectures. Plus, field is evolving so rapidly that the thing that worked like last week may not be the best this week. So I don't have anything favorite. I have large variety of architectures at my disposal that I'm used to, I have hands-on experience with. And like the question may be better. If you're facing this type of the task, what type of the network will you use? With respect to these limitations in terms of hardware and memory and things like this, and I'll probably can tell you like the answer for this every use case.
One of my mentors, a long time ago, he told me that if you only know how to use hammer well, then everything else looks like a nail. So that's what basically Vladimir is absolutely right. There are,
and you need to the slide. Okay, it's coming in.
So
You're there.
thank you for the introduction, and let me talk a little bit about Ancestry.com first. Most people know Ancestry as a provider of DNA testing for family history. And that's what most people are familiar with. Could you mute your mics, please? So, but this is only one part of the business. The Ancestry.com is fairly mature company. It's been around for about 40 years. Even probably close to 50. It started publishing a lot of family history books. Then it moved into publishing the CD-ROMs, then DVD-ROMs with family history and different records for different people. Then it created a website, created a DNA testing to help family history research, and now it provides also support for newspapers.com, Fold 3, which is a military record site. They also help like find the grave if you want to find where your ancestors buried. So this is a very diversified company supporting family research, helping people to really empower journeys of personal discovery to enrich lives. And in this slide, I want to demonstrate how the tree looks like. If you look at the Ancestry.com website and you start working with family history, you're able to create a family tree, a family history tree, how different ancestors relate to each other. And this is very interesting for a lot of people to learn more about those ancestors and find facts about those people, where they lived, how they lived, what they do, where they worked, who the children were. Some of them you may know, some of them you may not know from your, like you may not necessarily know how many brothers and sisters your grandfather had, for example. And so the ancestry actually helps by maintaining a very large databases of different facts about past events and past historical events and people. So, for example, we maintain a record for ship arrivals. Who arrived on which ship, what family. When the people emigrated to the United States to arrive to Ellis Island, we have very detailed record and scans of all the captain logs and documents like this. We may have records about military drafts. We can have military letters. There's a lot of, we have about 30,000 different databases that maintain a wide variety of different documents. And all historical documents, censuses, newspaper archives. So it's a very, very data-intensive operation. And as a part of the general ancestry mission, we help our users to extract information from those documents. So what does it mean? In this specific talk, I want to discuss how we can take the problem that we have at hand, one of the problems that my team addresses, and walk you through from the problem statement and through the data science solution and then implementation. Because often implementation is not less challenging than model development. A lot of people forget that developing the machine learning model or data science model is just beginning of the process. Those models need to be good. They need to create a good discrimination and create a good answering the question with low levels of error as possible, but that is not sufficient to build an industry-grade production system. We may want to process millions of images or millions of records, millions of requests per day, thousands per minute or per second often. The processing scale becomes costly. So the savings and using tools and technique to reduce the cost becomes important. There's a need to create a robust and maintainable resources in software. So you kind of allow things to fail, retry, start when we left off, when the system has been stopped, we need to maintain optimum resource allocation. We need to be able to auto-scale for variable input rates. The world is in general random, so we get a lot of changes, random changes in the true output. Sometimes it's very high, sometimes it's very low, and we need to maintain the appropriate level of resources to be able to process those things. So in my talk at the workshop in this conference, we're actually going through, look at all those problems and possible solutions, how we can really build industry-grade production system based on the machine learning models. And I think this is a very significant challenge still, even though, as previous speaker said, that some of the models become commodity, the engineering efforts still requires a lot of human power and a lot of activities to really make work it right. So now when we understand what is the, let's look at the pipeline data science part, the machine learning part of the models. So what we're going to look at, our problem, we have newspaper images, canned of newspaper pages, and we want to extract from this information, from those pages, obituaries of those published in those pages, and extract information from them about people who died, their family composition, age they died, when they born, all personal facts that we can from those obituaries. So this process requires several machine learning models. First would be actually detecting where those articles are. And as Vladimir just mentioned before, this is a very classical image segmentation process and object detection. We need to detect on the pages where those articles are and what type of those articles, because we don't want to process all kind of advertisement that we normally see in newspaper pages. We want to find only those articles that relate to people and specifically to obituaries. After we identified those articles, we want to run a classification step and actually determine if those articles are of the type that we need. Then we run text recognition, the NLP problem, to discover and understand what kind of entities is in this document. Is words in this document relates to people, to relationships, to locations, to dates. Next, after we did all this entity recognition step, the next step would be entity resolution. So we need to understand to what kind of people and what kind of entities that information belongs to. Is the date that we discovered, for example, belong to the death date or marriage date or birth date of the person? Is this belongs to the person A or person B that we recognized from this document? So it becomes an entity resolution problem. And then we need to prioritize and see if this information is actually needs to be delivered to the users in a different order based on their interests. Some users may be more interested in learning, for example, family history on the father's side. Others might be interested in learning on mother side, some might be interested in only female, others maybe only male side of the family. It is possible some people are interested in recent history, others might be looking for much more distant relatives who've been several generations away. So the prioritization will actually create a list of findings that we report to users in order that we expect interest them most. So as you can clearly see, it's not a single model that answered the question which seems to like be very simple. Like, can we extract the information about people that published in these articles? It turned out there is a set of data science and machine learning models that has to be executed in specific sequence to extract this information and deliver to appropriate users. And the next step would be to actually build the engineering system that will let us process hundreds of millions of pages of newspapers, scanned newspapers that we have, that will enable processing in reasonable time at reasonable cost, and at the same time maintaining the quality and integrity of the original data science models developed by scientists. So, and since I'm talking about the workshop that we're going to present at the conference, we're also going to not only review all of those requirements and all those aspects in much more details, but it's not going to be a theoretical presentation. It's going to be a hands-on work where you're actually going to build some of those technologies by yourself and be able to produce models and results using AWS, a cloud-based solution, and actually see how different inputs and variables can change the output, can change the results that we get, and get us and learn how to deploy. And hopefully you will be able to learn from this workshop and take it to your workplace or your classroom and be able to replicate it and have an idea and skills how to create a similar models and similar deployment strategies going forward, and help your company, your school, or in an industry in general to move forward and create much more sophisticated solution. We do need a lot of advancement in technology so we can, as a society, reap benefits from rapid development of data science and machine learning. So that's about what I have, about 20 minutes. Do you have any questions?
Actually, I have a question. Do you work with Russian articles, or I mean, do you work with articles only in English language, or you also support Russian language?
Right now it's only English language, but we're working on French and Chinese right now. Russian is kind of right now is a second kind of level of complexity that we're looking at.
Okay, thank you.
Are there any other questions?